My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and very good morning to all those who are watching this program live from USA. So today we are going to welcome you all through a joint session between our Department of Physics, Pabna, University of Science and Technology, and Department of Physics and Astronomy, University of Utah, USA. We have with us here today Dr. Carsten Rott, Professor, Department of Physics and Astronomy, University of Utah, USA, and he has already connected with us. So I'd like to welcome our speaker, sir. Good morning and good evening to here. Thanks for accepting our invitation, sir. And before going to you, I'd like to introduce you with our student and the viewers. So, dear student and viewers, I think you have already come to know the title of the today's International Physics webinar. That is very exciting and interesting too. So, our today's title of this, our today's International Physics webinar is the Exploring the Universe with High Energy Neutrinos. And our speaker is Dr. Carsten Rott, Professor, Department of Physics and Astronomy, University of Utah, USA. As you can see, he has completed his PhD from the Department of Physics, Purdue University, and his project was a search for solar bottom quarks from gluino decays at CDF, and you can see that he studied physics as an undergraduate at the University at Hanover and went to receive a PhD from the Purdue University for work on the colloidal detector at Fermilab, CDF. Rott has been a member of the IceCube Neutrino telescope since the start of the construction of the December in 2005. As a postdoctoral researcher at Penn State University, he performed detector calibration and verification efforts for IceCube. For this task, he traveled multiple times to the uh, Amsterdam Scots South Pole Station. Later moved to the Ohio State University as a senior fellow of the Center of Cosmology and Astroparticle Physics. In 2013, he became the assistant professor of the Sakyonggan University in South Korea and was subsequently promoted to a senior associate professor. In 2021, Rott became a professor at the University of Utah and has been appointed to the Jack W. Keuffel Memorial Chair. Rott will hold the chair through December 2015. And you can see his research. Uh, he has a several publication, and I think you will enjoy our this session because this is very exciting talk on neutrino, high energy neutrinos. So thanks, sir, for giving us this opportunity. It's your time, so you can start your session.
Yeah. Okay, thank you very much. Thanks for the nice introduction, and it's a pleasure to be here. It's actually my first talk I give in Bangladesh, unfortunately
Yes,
virtual, but I hope to be there at some point in person when we can
yeah,
travel
in
again.
future, we can invite you after the
Yeah.
pandemic. Thanks, sir.
Yeah,
You can start.
I really hope so. Yeah. Yeah, and so today I would like to take you to the South Pole, to Antarctica. That's actually where we have built the IceCube neutrino telescope, and this is actually what you can see here. You can see my pointer also. So this is actually our counting house at the geographic South Pole. That's where the data is collected with the IceCube neutrino telescope. And in my talk today, I'm going to talk about exploring the universe with high-energy neutrinos. And before coming to high-energy neutrinos, or how we are using high-energy neutrinos to explore the universe, I would like to go back and introduce the cosmic ray problem, which is closely related to why we have built this detector. So this is the outline of my talk today. So I will first introduce the cosmic ray mystery, then introduce neutrino telescopes and IceCube, present some selected results of the experiment, and then also give an outlook in the future. And I have, since many undergrad students are connected to this talk, I also focused my talk a bit on what students are actually doing on an experiment like IceCube. So let me start by introducing the cosmic ray mystery. So basically, this goes back to Victor Hess, who tried to answer the question where ionizing radiation is coming from. So at the beginning of the last century, it was observed that there's ionizing radiation, and it was not really clear where this radiation is coming from, if it's coming from the Earth, for example, through nuclear decays, or if there's any radiation coming from the cosmos. And what he did in some very pioneering experiments using electroscopes on balloons, he showed basically that this ionizing radiation increases with altitude. And he took some quite daring flights that were also quite dangerous to himself, or put himself in danger, where he went up to 4 or 5 kilometers, so of course without any oxygen at that time. And but he succeeded in showing that the ionizing radiation increases with altitude. And today we understand much better what he has observed, and what he basically saw were the remnants of a cosmic or high energy cosmic ray interacting in the higher atmosphere of the Earth. So when an energetic particle, and for now you can think of this as a proton or as a nuclei, enters the atmosphere, it interacts with the atmosphere in a collision and produces a particle shower. And this is an image of such a particle shower. And here's basically Victor Hess in his balloon, and he undertook basically these flights in around 1912. And in 1936, actually, he received the Nobel Prize for this discovery of the high energy cosmic rays, or the cosmic rays. Now, you see, okay. So that's basically Victor Hess here in his balloon. And today we can actually measure these cosmic ray air showers more precisely using surface array detectors. And there are actually 2 leading experiments, the telescope array and the Pierre Auger observatory. Telescope array is actually located very close to where I am. It's located in Delta, Utah, and we have about 500 of these surface array detectors. So these are scintillation surface detectors that detect the radiation that's generated in this high energy cosmic ray air showers. And in addition, we also have some fluorescence telescopes that look for the fluorescent light that's emitted when cosmic ray air showers interact in the atmosphere. And this is actually a very impressive experiment. Each of these scintillation surface detector has basically a distance of 1,200 meters to the next one. So this is actually a very large array, roughly actually 2,000 or 200,000 acres in size that's covered by this detector. Now, through these measurements from Auger and telescope array, we have actually, and many other experiments, we have actually developed a very good idea about this, the cosmic ray spectrum. And this is actually the energy spectrum of the cosmic rays that we observe. And you can see we have ranges here of the energies of the particles, ranging from GeVs to extremely high energies like EeV and beyond. And understanding this cosmic ray spectrum is a presentation by itself. But what I'm actually personally most interested in is this highest energy part here. And so let's focus a bit on this highest energies. We see that this cosmic ray energy spectrum extends to energies of 100 EeV, so these are 10 to the 20 electron volts. Just to give you the scale here, this is roughly 10 to the 7 times larger in energy than the energies that's carried by the protons in the LHC beams. And the question that I want to really answer is, where are the cosmic accelerators that can accelerate particles to such extreme energies that are much higher than the energies that we can generate here on Earth with accelerators? Now, answering this question is actually not that easy, and this is actually where neutrinos come in, because as you know, the high energy cosmic rays are charged particles. So if you think of it as a proton, these cosmic ray air showers, these particles, of course, bend in the galactic and extragalactic magnetic fields, so that it's very difficult to actually point back where they are coming from, even if we observe the cosmic ray air shower. Now, the sources of the high energy cosmic rays, and there are many candidate sources here, from active galactic nuclei, gamma ray burst, supernova remnants. At these potential sources, we expect that particles get accelerated in jets. In these jets, the protons can interact with energetic photons or with other material in the jet, and then in pp or p gamma interactions, pions are produced, and when pions decay, they produce neutrinos or gamma rays. So if a neutral pion decays, it produces 2 gamma rays, and if a charged pion decays, it produces neutrinos as part of the decay. Now, observing gamma rays is also a bit more difficult, since gamma rays interact with the interstellar background light and also can easily get absorbed. The neutrinos, however, since they are weakly interacting particles, travel directly to us, and therefore if you observe a high energy neutrino from a cosmic source, we can actually use that to identify the accelerators of the high energy cosmic rays and solve this cosmic ray mystery. Now, how do we detect a high energy neutrino? So when an energetic neutrino interacts via a charge current and interaction, it produces, in this case, I take an example of a high energy muon neutrinos that interacts via a charged current interaction. So with the W boson, it produces an energetic muon, and this energetic muon then travels basically with the speed of light. If this happens in water or ice, where the speed of light in the medium is actually lower than the speed of light in vacuum, the muon will generate shrink of light. This is a very characteristic radiation, and you can see this, for example, if you stand next to a nuclear reactor and you look into the water, you will see this faint blue light, which is a shrink of light that is produced by a relativistic particle traveling through water or ice. Now, this shrink of radiation is also emitted at a very a specific angle. So for ice, this is actually 41 degrees. And if we have a precisely timed sensor array for detecting this shrink of light, we can then actually reconstruct how this muon traveled through the ice or through water, and then use the direction of the muon, to infer where actually the neutrino came from. Now, this is actually pursued or utilized by a number of experiments around the world. These are large neutrino detectors or large neutrino telescopes that basically use this detection principle, starting from large water Cherenkov detectors that are built in excavated cavities. This is, for example, the Super Kamiokande experiment that has a fiducial volume of 22.5 kilotons, and then a large number of these 20-inch PMTs to observe Cherenkov light that is emitted when basically the neutrinos interact in the detector. There's a plan for building actually roughly 10 times larger detector now, which is the Hyper Kamiokande experiment. And also there are plans underway for a Korean neutrino observatory that will use a similar detection principle. These are all detectors that are using a cavity that is excavated. Now, if you want to build a very large detector, however, it is very beneficial if you use an optical or a medium with good optical properties that is naturally occurring, because you're limited in size of these detectors by the cavity that you can construct. So therefore, a number of experiments have chosen to use an optical medium that is naturally occurring and has good optical properties. And this is done, for example, by Lake Baikal, using the water or the clear water of the lake there. It's pursued by several experiments in the Mediterranean Sea using the deep clear water of the Mediterranean. And by far the largest neutrino detector is actually the IceCube Neutrino Telescope, which is located at the geographic South Pole and uses the ultra pure ice there. And you can see a picture actually here from the South Pole from our drill team that has actually drilled holes into the ice at the South Pole to deploy these sensors. And actually, this is a picture of our detector completion, where you can see down here. Down here, you can also see some champagne on ice that is now covered up by this bar, but this is actually when we completed the last deployment. So the IceCube Neutrino Telescope is actually by far the largest detectors of these, which has an instrumented volume of 1 gigaton. So it's 1 kilometer by 1 kilometer by 1 kilometer in size. Okay, let me skip this and move to the IceCube Neutrino Telescope. This is actually the detector site at the geographic South Pole. This is the Amundsen Scott South Pole Station. This is the IceCube detector site from this aerial view. And here you can see actually the IceCube counting house, which is located on top of this surface here. This is actually where all the data gets collected. And this is actually one of my students, Sonjin In, who went to the South Pole and helped also with the work there. And yeah, recently showing a poster here for also advertising Sangyungan University, where I was basically also the last 7 years. Actually, I'm still also associated with Sangyungan University. So Sangyungan University, or let me introduce IceCube collaboration actually. So we are international collaboration of 300 scientists from 12 countries. Most of them in North America, US, and Canada, and then also in several European countries, and in Asia we have Japan, Korea, and then also Australia and New Zealand. And I started the group actually in 2013 at Sangyeong University, and then as you mentioned, I moved to the University of Utah. Now, these are just some pictures of my team here, just to introducing them. Now, this is a picture or a schematic view of the detector. So we have chosen the geographic South Pole as a detector site because the ice at the geographic South Pole is about 3 kilometers thick. And so we can use this very thick ice layer to effectively build our neutrino detector. So the IceCube detector or the sensor modules are located basically 1.5 to 2.5 kilometers down in the ice, and we have used a hot water drill to basically drill down to the depths of 2.5 kilometers and then deploy strings of optical sensor modules. And this is a schematic drawing of such a sensor module that contains a 10-inch Hamamatsu PMT together with some digitization electronics. And here you can see on a desk next to me such a module. And we have basically each of these strings has 60 of these modules attached to it, and then we have 86 strings. These strings are spaced 125 meters apart, and vertically they are 17 meters apart. We have in the central region a more densely instrumented array that allows us to achieve a lower energy threshold. So with this denser instrumented array, we have an energy threshold of roughly 10 GeV, while this main array has a threshold that's closer to 100 GeV in energies. Once these detectors are deployed in the ice, the environment is actually very stable. So 99 or 98% of our sensor modules are basically functioning perfectly. And we have a high detector uptime, so basically more than 99%. The detector is operating, and this is of course also important in case there's a supernova in our galaxy. We want to observe the signal, so that's why we also want to have these very high uptimes. Okay, let me move on. So this is just to introduce the type of events that we are seeing. So most of the events that we are seeing is actually caused by downgoing muons. So these are produced when high-energy cosmic rays interact above the detector and produce an energetic muon that passes through the detector. What we are most interested in are, of course, the detection of neutrinos, and for most of the neutrinos actually that we observe are actually caused or generated in the Earth's atmosphere. And the easiest way to observe or identify a neutrino is actually to look for an upgoing event. That means, for example, if a neutrino is generated, it passes through the Earth and then interacts below the detector, generating a high-energy muon that's upgoing. These atmospheric neutrinos are the dominant neutrino signal that we observe. We are, of course, most interested in astrophysical neutrinos, so neutrinos that are generated beyond our solar system, and to identify a neutrino, an astrophysical neutrino, or distinguish an astrophysical neutrinos from atmospheric neutrino is of course only possible based on a statistical way or statistical method. And then observing neutrinos in downgoing directions also possible if these interact directly in the detector. Otherwise, we are quite swamped by the downgoing atmospheric muon signal from cosmic ray interactions. To give you a sense of scale, we detect roughly 10 to the 11 atmospheric muons per year with the IceCube neutrino detector, roughly 100,000 atmospheric neutrinos, and about 100 astrophysical neutrinos. And sorting out these 100 astrophysical neutrinos out of this background, that is the real challenge of the experiment. Now let me go over some selected results and introduce the science program. So first of all, the science program that is enabled by the IceCube Neutrino Telescope is extremely broad. It ranges basically from astroparticle physics to particle physics, cosmic ray physics, searching for supernova, and also it involves a component of glaciology, because we have to actually understand the properties of our detector medium very well in order to reconstruct our events precisely. Now let me focus on the search for astrophysical neutrinos. There are actually 4 different ways how we can look for astrophysical neutrinos. The first one is basically to look for a clustering of neutrino events on the sky. The second one is to look for a short neutrino burst that is associated with a small region of the sky. So this could be like for example, some transient event. We can also look for a combination of a neutrino event with some other messenger particle. So for example, if we are looking for neutrinos coming from the direction of a GRB, so a gamma ray burst, so then you can correlate a neutrino signal with a gamma ray signal. And the last one is actually to not look for an individual source, but collectively look for the neutrino spectrum that is generated by a number of sources. And we expect actually that the energy spectrum from these neutrinos of astrophysical origin are different from those that we observe from the Earth, from the atmospheric neutrinos. Now let me go into these different ways now. The first one I want to start is a diffuse astrophysical neutrino search. So this is actually looking collectively for the sources, or collectively for neutrinos generated by a number of sources. Now, the first, and unfortunately this animation doesn't show the first event that we observed, and actually was or that gave us some indication of such an event, is actually a high energy neutrino event that was observed now about 10 years ago. And this event actually had an energy of 1 PeV, which is of course much higher already than the energies that are generated by at LHC, for example. And this event is extremely unlikely by itself to come from the Earth's atmosphere. So we then actually mapped the observed neutrino energies of a class of these high energy cascade events. These are actually events that produce kind of a spherical light signature in the detector. We mapped the energy of these events and compared this to the expected background from the atmospheric neutrinos and atmospheric muons. And you can see here in red and purple basically the expected backgrounds, and then these are our data points, and you can see a clear excess of events. And this we were able to show that this fits actually well to the expectation from astrophysical neutrino events. These events, if we map them on the sky or point them back, they are actually isotropically distributed all over the sky. So Now, independently of that, we actually do several different analyses that look for an astrophysical neutrino flux, and we can use our detector for that in different ways by exploiting different signatures of these events. So the first one is these cascade-like signature. These are more spherical events. These are generated typically when electron neutrinos interact in the detector, but also can be caused by neutral current events or tau neutrino interactions. We have another signature that is generated when muon neutrinos interact, basically below the detector. So we get a kind of a track that passes through the detector. And then also most recently, we looked for events that are near the edge of the detector. And on this plot below here is actually the energy spectrum that we obtain with these three complementary ways. And this actually shows us a kind of a consistent picture of this diffuse astrophysical neutrino flux. Now, we can also look for correlated events. This is actually going into multi-messenger science, so looking for a correlation between some astronomical event and observation of a neutrino. And for this, let me actually step back a bit and talk about a very exciting event, which is called actually the IceCube 1709-22A. So this 17 actually stands for 2017. This is the month, so September 22nd. This is actually when this event was observed. So we observed 290 TeV neutrino passing through the detector, and whenever we detect such an energetic event, we actually alert other telescopes to about the direction where this neutrino came from, so that they can point their instrument in that direction and check also if they see any interesting events there. And it happened that actually in this case, two other instruments saw energetic radiation from the same direction. Now, this is maybe also to interest to some of the students. If you are interested in these alerts, whenever IceCube detects such a high energy neutrino event, you can actually download a cell phone app, which is called the IceCube AR, the IceCube Augmented Reality, where you can actually display these events. And this is like an example of me and my postdoc, Christoph Tönnes, in my office in Korea, actually, where we displayed such an event using this app. Okay, so then when we detected this IceCube 1709-22 high energy neutrino event, it pointed back to a region of the sky, and in this direction, both MAGIC and Fermi actually detected an excess of gamma rays, and this map actually showed where IceCube located the neutrino from. This is actually event display of the IceCube event, and then this is where both MAGIC and Fermi located or detected energetic radiation. So there was a coincidence between these detections, and these were linked actually to a flaring blazar. This is actually the location in the sky here. So if you look at the night sky and see Orion, you can find this location here. This is actually where this blazar is located, where we detected the neutrino from. Now, since we knew the location, we actually also asked ourselves, did we in the past see any neutrino signal from this direction? And we looked actually over time, going into our archival data, And we saw that actually during 2015, there was another flare in neutrinos. And this flare of neutrinos was actually not accompanied by any gamma rays. So this is so what we learned from this is actually that these neutrino signals might not be always correlated with gamma ray signatures. Also, the object itself that where we observed this high-energy neutrino from, a blazar, has been regarded in the past, of course, also as one of the primary potential sources of high-energy neutrinos, and we have done several searches in the past, and those always turned out negative. So this actually points to that this is maybe a new class of blazar, or that the emission of neutrinos from blazars is basically not, of course, not steady, but maybe only associated with a subclass of them. This is actually what a blazar is. So a blazar is a supermassive black hole at the center of a galaxy, and you have basically jets associated with these infalling material to the supermassive black hole, and then generating these jets. And if this jet actually happens to point directly at Earth, this is actually when we call this a blazar. And this is, of course, an artist impression, so we don't actually have any real picture of this. Now, the event that we observed, the TXS 0506, is actually a very interesting object. So this is actually located at 1.8 gigaparsecs, or a redshift of 0.33. So this is actually quite far away, and with cosmic rays or gamma rays or high energy gamma rays, you can actually not access these distances, because gamma rays interact with extragalactic background light and CMB, and also the high energy cosmic rays actually interact with also with the CMB, so you could not observe an energetic cosmic ray or gamma ray directly from this direction. There are also several other candidates for point sources that are emerging. So in our point source search, basically mapping neutrinos all over the sky, we have one object that starts to stand out more significantly. This has now an excess of 2.9 sigmas. This is NGC 1068 or M77. So this is actually a picture of that. And then also another potential source is actually tidal disruption events, where we have seen also some interesting correlation actually between some high energy neutrino events and then these tidal disruption events. So this is actually not a result from the IceCube collaboration, but some external team actually associates this, and the IceCube collaboration is actually also very seriously looking into this. Let me maybe just skip this and move on. One of the interests that I personally also have is, are there any signals of new physics in these high energy neutrinos or astrophysical neutrinos that we observe? For example, there have been some claims that this astrophysical neutrino spectrum that is observed by IceCube can be understood better if we introduce some heavy decaying dark matter. And there are a number of papers that suggested that. And actually one of my former students, Hrvoje Dučmović, he looked into this, and he did an analysis where he looked if the high-energy neutrinos that we observe over the sky, if they are clustered in a way as we would expect from heavy decaying dark matter. And he didn't observe this, so therefore we were able to set actually a bound on this heavy decaying dark matter. And this is actually the limit plot that he produced. This is as function of the dark matter mass, ranging basically from TV range to PV range and beyond. And then this is the dark matter lifetime. And this is the IceCube bound here compared to some other experiments. And you can actually see that he was able to do the most sensitive test and has the most stringent bound produced here, excluding lifetimes of 10 to the 28 seconds. Another analysis, and I also want to introduce this because this is actually one of my students doing this analysis. So I think it's interesting also to the students attending this seminar that they see kind of what students work on. So he's actually looking for a signal of neutrinos that could be generated when high-energy cosmic rays interact in the solar atmosphere. And we recently observed actually for the first time that there is high-energy gamma rays are associated also when cosmic rays interact in the sun. So this was recently observed in Fermi data, and this is actually shown here as the distance of the sun. This is the data, and then it basically shows a disk emission and some inverse Compton emission that can be fitted there. Now, my student Sonjin In, he looked actually at the neutrino data using the IceCube detector. Actually, when you are at the South Pole, it's a very interesting phenomenon that the sun basically just rotates in the sky, and you have you basically have then one sunset that occurs basically in April, and then you have a sunrise that occurs in end of September, I think. And so what he actually looks at is the data when the sun is below the horizon, so when it's basically dark at the South Pole, because that means if he looks for high energy neutrino events, then those pass through the Earth and they can effectively reject the backgrounds that are associated with from cosmic ray air showers. Now he was able to actually set a stringent bound on this flux from the sun, and one of my new students, Gerrit Rollinghoff, so he's now working on improving this analysis, and we hope actually to find a signal of this, which has never been observed. So now, let me, in the last few minutes, let me also talk a bit about what are our future plans. So what's next? So this is a Gen 2 penguin. And the Gen 2 is actually also the name of our future experiment that we plan to build at the geographic South Pole. This is actually called the IceCube Gen 2, Generation 2. And this is the current detector, which started construction in 2005 and was completed in 2011. And we have been taking data for 10 years now with this detector. This is basically the red region here. We have plans for an upgrade, which is actually under construction now. The original plan was actually to deploy this 2022, 2023. Due to COVID, access to the South Pole has been limited, so this will be shifted a bit later. But we hope to have actually, by 2025, to have data from this experiment. And then for the Gen 2 detector, we plan to build a 10 times larger detector. And let me just mention a few words about the IceCube upgrade. So for the IceCube upgrade, for IceCube, actually, we use these IceCube digital optical sensor modules to detect the shrink of light. And for the upgrade, we're using some new type of modules, which are called MDOMs, which have multiple small PMTs. So it allows us for the directional detection of light. And then we also have modules that are called DEC, which basically have two PMTs that are back-to-back, one facing up and one facing down. And this makes for more efficient light detection, and also allows for to give some directionality actually where the light is coming from, which will help us to better reconstruct the neutrino events. The primary science goal of the IceCube upgrade is actually to look at neutrino oscillations, primarily testing the PMNS matrix, which is a leptonic mixing matrix. And if basically what we want to see if this mixing matrix is unitary, and if it's not unitary, that would mean or could give us indications that there's some new physics or some maybe force neutrino that's existing besides the three known neutrinos. Also, we can very effectively perform neutrino oscillation experiments, because this detector accesses an energy region of about 1 to 10 GeV. This is where atmospheric neutrinos can be very effectively used to look for neutrino oscillations. And this is a plot that actually shows the neutrino oscillation parameters, delta m squared 3,2, and then delta theta, sine squared 2 theta, sorry. And already you can see that the IceCube measurement, which is in yellow here, is very competitive with other experiments that look for neutrino oscillations that are actually designed to just look for neutrino oscillations. So even though IceCube was not designed to look for neutrino oscillations, we have one of the world's best measurement on the neutrino oscillation parameters. And with the upgrade, we actually expect to go, to have really some of the world's best measurement of neutrino oscillation parameters. Important actually for this measurement is to really understand the properties of the ice. This is actually also one of my priorities, to better understand the ice properties, our detector medium. For this, actually, we have designed a new calibration system. This actually uses these small miniature cameras that will be integrated into all the new optical sensor modules that will be deployed for the IceCube upgrade. And actually, one of my students recently went to South Pole to actually test one of those systems there. This is actually a picture taken with this camera with our PI, Francis Halsen, at UW-Madison, and like some other group of people who are also involved in this project. And this is some of my team in Korea, actually, where we did some testing of the camera system in a swimming pool, and these are some of the measurements that we did with that. And the idea is actually that we want to use the cameras and some LEDs to basically better track the light, how it travels through the ice. Now, these calibration cameras will be only very rarely used, because they are, of course, not used to detect the shrink of light, but they are just used to better understand the ray tracing of how the light travels through the ice. And then we have run already some simulations that actually shows us that understanding the ice properties is extremely important. This is actually as function of the deposited energy, the median angular uncertainty that is associated with high energy cascade-like events. And you can see that these high energy cascades, so these are electron neutrinos, have an uncertainty of 10 10 to 20 degrees. So this is a median angular error. And if we have a perfect understanding of the ice properties, we expect this to be actually much lower. So in some cases, you maybe have up to a factor of 6 improvement in the pointing. And then, of course, if you can point neutrinos better back to where they came from, that also means you can better do multi-messenger science, pointing back or correlating that with other events like a gamma ray burst. Now our plan is then, once we deploy this new calibration system, to better calibrate the detector, and then we can retroactively analyze actually the already existing IceCube data to see if the already collected data has some maybe interesting events already in them. Then for IceCube Gen 2, we also expect to better identify potential sources of the high energy astrophysical neutrino flux. And this is sort of the money plot here that shows actually the effective neutrino luminosity and the local density of different sources. And they are listed here, starting from galaxy clusters, AGNs, BLAC objects. And basically for each of these objects, we know their kind of effective local density. And we know that from the diffuse astrophysical neutrino flux that we observe, we are falling somewhere in this band, but then through point source searches, we can basically extend the sensitivity for IceCube and then IceCube Gen 2 to individually check these sources and identify the dominant source of the high energy cosmic rays. Okay, with that, let me actually end and summarize. So high energy astrophysical neutrinos have opened up a new window to the universe. We are now able to observe the universe using high energy neutrinos, and we have first hints of sources of the high energy cosmic rays associated, for example, with the TXS event that we observed. Neutrino telescopes are really multi-purpose experiments that have a very broad scientific program, and I mentioned 2 examples here also: the search for dark matter and the search for high energy neutrinos from the sun. But it's a really broad, exciting program. Neutrino astronomy is really a critical part of multi-messenger science, so correlating neutrino events with other messenger particles, such as gamma rays or cosmic rays, or also associating them with gravitational waves. So this is something that's a very active field and ongoing. And then the IceCube upgrade is now under construction. We are building new sensor modules. Actually, 700 modules will be built and deployed in the near future. And with that detector, we are looking forward to many new discoveries in the near future. So thank you.
Yeah, thank you, sir, for your wonderful and exciting presentation, sir. So we have got few questions in inbox and in comment section. So
Yes.
if you allow, we can start our discussion session.
Yes.
So first question from inbox. So what is astrophysical neutrino flux?
Yes. So let me go back. Astrophysical neutrino flux. So basically, when I refer to astrophysical neutrino flux, I actually refer to this spectrum. So here, so this astrophysical neutrino flux is actually the the flux of the neutrinos that are coming from astrophysical sources, so from beyond our solar system. And we basically expect that astrophysical neutrino sources have a spectral index of roughly e to the minus 2 or e to the minus 2.7. This is just from the acceleration models at the sources, and what I refer to is basically this flux spectrum that we observe. Yeah.
Yeah, thank you, sir. We have another question. So, can neutrino help us to understand dark matter and dark energy?
Yes. So high-energy neutrinos can help us to understand actually the particle nature of dark matter. So if and let me go back to this example that I showed here. Here we have different dark matter particle candidates, and if they decay, they are expected to produce neutrinos either directly or through sequential decays. And we can probe actually for these signatures of dark matter with IceCube, basically indirectly looking for dark matter based on the distribution of the high energy neutrinos that we observe. Yeah.
Thank you, sir. We have another question. So, the next question from comment section. So, what is the exact size of neutrino? Is it even smaller than a quark or an electron?
Yes, yeah. So the so for the size of the neutrino, I mean, it's basically a neutral weakly interacting particle, and you can think of it basically as a point-like particle. I mean, sometimes we say the neutrino is kind of the partner or of an electron because it's the same group in leptons, and an electron is basically also a point-like particle. So
Okay, sir. Thank you. So there is another question. So could neutrinos shed some light on why the universe has so much more matter than antimatter?
yes. Um, um, yeah, with that, I think I'm trying to think of a good answer here, but I don't see there's a direct way how observing the high energy astrophysical neutrino flux will help us answering this matter antimatter asymmetry that we observe. Yeah.
Sir, this may be the last question. So where do the highest energy neutrinos in the universe come from?
Yeah, that is actually the big question that we want to answer, and this is still an unanswered question. So
Yeah.
we have this first indication that we observed high energy neutrinos from the flaring blazar, but as I mentioned, blazars cannot describe the diffuse astrophysical neutrino flux that we observe. So there are new sources or other sources which we have not yet discovered. So there's actually a lot still to do, and also for students who are excited about this, I mean, I encourage you to enter this field, and there's still a lot to learn, and we don't really know the answer yet where the high energy astrophysical neutrinos are coming from in general. Yeah.
Okay, sir. Thank you for your wonderful and exciting presentation and discussion session, sir. It was a great webinar with you. I think this is a great opportunity for us students and the viewers to learn a lot of things about the neutrino physics and the future experiment of IceCube. So thanks again for giving us this opportunity to attend such an important webinar. And we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So bye
Yes.
for today. And in future, if we have a opportunity, and after the COVID, we'll definitely invite you for a face-to-face session, and that will be very exciting. And before end, I've got another question. So this may be the last question. If you allow, I can take this.
Yeah.
So how neutrino winds occurring during the R process nucleosynthesis?
This maybe goes beyond really what I talked about. So I'm not sure if I can answer that question
Okay.
here. Yeah. Yes.
Okay, sir.
Yeah.
So bye for today.
Yeah.
Have a
Okay.
nice day, sir. Good
Yeah.
night for here.
Thank you. Yeah. Bye bye.
Bye.